So I'd like to summarize a little bit, since what these videos contained regarding constant acceleration, this is really the foundation of kinematics. This is, in a way, the ending point of the study of one-dimensional motion. So the first thing to again stress is that everything we've talked about here is true for constant acceleration. If you find yourself in a situation where you don't think you have constant acceleration, you might want to look for a different way to approach the problem, or you'll actually need to do the integration of acceleration itself. So there's three plots to think about at this point: a plot of acceleration versus time, velocity versus time, and position versus time. If you have a constant acceleration, that's going to be a horizontal line. That means the change in acceleration is 0 with respect to time. You might have a piecewise situation where you have a horizontal segment and then another horizontal segment, and that means you would need to treat each of those segments separately. On the velocity plot, you're going to have a straight line where the slope of this line is going to be your acceleration. Remember that if you know acceleration, there's no way to get what your initial speed is. You'll want to carefully read the problem to make sure that you understand what your initial speed is, possibly at 0 if your object is starting, for instance, from rest. Now, if we then integrate our straight line segment, we're going to get a parabola. And again, we need a different piece of information to know what our starting point is. And the slope of this parabola is going to be giving you the speed at any one point. So this is when we talked about instantaneous velocity, since each of these times has a different velocity, and the slope here would give you the velocity at that time. Now, one thing to mention is, since acceleration is therefore the second derivative of position, that in this case, because this is concave up, that represents a positive acceleration, and if it was concave down, that would represent a negative acceleration. So please be careful regarding accelerations that are, say, speeding up or slowing down, pointing to the left, pointing to the right. We can always talk about positive or negative accelerations in terms of the concavity of our position. So this is again all for movement in a straight line, which means one dimension, and we will be expanding this to 2 dimensions, which is why I keep stressing the one-dimensional aspect of this, is that when we work with 2 dimensions, we actually need to set up these plots, or for instance the equations, separately for what's happening in the x direction and separately for what's happening in the y direction. So that's why the one-dimensional aspect of this is so important. Mathematically, there are 3 equations we need to worry about. This equation is relating the final velocity to the initial velocity, our constant acceleration, and the change in time, the time interval. Now note that here we have those subscripts of s, which is a generalized coordinate. Again, that could be x or it could be y, but the coordinate needs to be the same on every single one of these. Now we then have 2 versions that relate to position. This one is the final position is equal to the initial position plus that initial velocity. Don't forget about that. Times our elapsed time plus 1/2 times our acceleration times the elapsed time squared. And again, this term came from really integrating acceleration twice. So this derivation I showed you in a video. The third equation is what I call the time-free kinematics equation, because time does not appear in it. Instead, you explicitly have your final speed and your initial speed. And note that they're squared, which is why I can say speed in a way, in that if it was negative, that negative sign would square out. So again, that was derived for you in the previous video. Now, the important thing to know is that these equations completely fail if the acceleration changes. So if you have a situation where you have changing acceleration, you must consider each section separately. If you have a continuously changing acceleration, you would actually need to do integration. You might instead just have one value of acceleration and then at a later time a different value of acceleration. And in that case, you can only use these equations for the time interval limited to a single constant acceleration. So now I'd like to discuss a little bit about how you're going to approach problem solving for kinematic situations, which just means physics of motion. So first of all, you want to choose a model. And the model we've been talking about here is constant acceleration. Note that another model we've talked about is uniform motion, which is when you have zero acceleration. So if your acceleration is zero, this model is actually more complicated than you need. So if you have zero acceleration, please choose uniform motion rather than constant acceleration. On the other hand, if you do have a non-zero acceleration, which is constant, or at least is piecewise constant, you want to consider the model that we are talking about here. Now, we can choose to do a pictorial representation, such as a sketch or a motion diagram, and you are strongly encouraged to use that approach to really make sure you understand what's happening. Along with that is a graphical representation, for instance, plots of acceleration, velocity, and position. And especially if you've been given one of those plots, you probably want to generate those other plots to make sure you understand what's happening. Now, you aren't required to create a graphical representation, especially if you have a pictorial representation that you think is helpful. Where the graphical representation is going to be most helpful is if you have motion that is only constant acceleration for a limited amount of time, and then it's becoming a different constant acceleration. So for instance, in this scenario where you initially have a positive acceleration, and then suddenly you have a negative acceleration, and that at a time later you have zero acceleration, if you've been told about a scenario where this describes it, it's really helpful to draw these plots. And in this case, this would be your acceleration plot, and you could then generate a velocity plot based on it. And that's going to help you understand how the math of these situations are going to connect. Because you actually are going to need one set of equations for this first section, another set of equations for the second section, and possibly a third set of equations for that third section. And they do relate together, especially via velocity and position. However, you actually have to set them up separately since the accelerations are separate. So again, these are the three equations that we're largely using here. Do please use x or y rather than just the generic s, but this is one way of just showing that that can be any one-dimensional direction you want. And again, here typically I'm saying initial and final, but what's important to know is, for instance, in this situation I have an initial here, and then I might call this final 1, but that equals initial 2, right? This moment in time. And then this moment in time is my final for equations 2, but that equals initial for equation 3. So please think about that carefully, that you don't just want to use I and F, that especially in these situations where you have multiple points of time that are relevant, you need to actually have careful notation across multiple sets of equations. Finally, always make sure that you assess whether your answer is reasonable. The units are very important, and the units here you can actually check to see that they're going to work in general if you're plugging in the correct units, and make sure that the significant figures are correct. And again, separate videos have covered how to do that correctly. Finally, make sure that your answer is reasonable, that I try very hard to give you problems that have real-world, valid speeds, positions, accelerations, lengths, things like that. So if you calculate that the stopping distance for a car is 1 nanometer or thousands of kilometers, you've probably made a mistake. So please check that and always make sure that it answers the question. The question might be a distance, but it might not be a final position, it might be a displacement, or it might be a time in the middle rather than an end time. So do verify that you're really answering what the question is, reporting what you were supposed to report, rather than just picking something that looks like it's correct. So to really briefly summarize what has happened in these acceleration videos that have been quite long, first, to know that constant acceleration will look like a straight line on a velocity plot, and that will look like a parabola in position. So be careful about that, and again, you can go back and forth between these using calculus. Finally, there's going to be 3 equations that you're regularly going to use, and in this case, these are all for constant acceleration. You need to explicitly use calculus if you have non-constant acceleration, or break it piecewise. So one equation relates your velocities, initial and final in time. what I call, just in general, the kinematics equation relates your initial and final position, so your displacement, your initial velocity and time, but then the time-free kinematics equation gives you displacement, initial, final velocities, and time doesn't appear in it at all. So this is really important, and it can get quite challenging, so please make sure that you understand this, as these ideas from kinematics are going to come up all semester and even into the second semester of physics.